Okay, so let's take a look at question 3 from the 2013 paper. Still looking at organic chemistry at the moment. So it's a flow diagram style question. And students who know their overall scheme of how all the families link together for level 2 organic chemistry, or level 3 for that matter, will enjoy doing questions like this. If you haven't memorized the key reagents to get from one family to the other, then you really have no chance of doing questions like this. So there's a certain amount of rote learning needs to be done. And the first family that you're starting with is butyronene, so it's an alkene. So this is butyronene, an alkene. And then you're ending up with a secondary alcohol here. And that secondary alcohol would be butan 2-ol. The alcohol is in the second position. And it's a secondary alcohol because the carbon which has the OH group attached to it has two other carbons directly attached to it. And then you're going from your secondary alcohol using some sort of reagent to form a haloalkane. So this is the secondary haloalkane. That haloalkane would be called 2-chlorobutane. And then the final reaction using reagent C reforms an alkene, but this time it's but2ene. So you've shifted the position of the double bond, which could be useful in organic synthesis. And the question is as follows: use the reaction scheme above to complete the following table to show the formula of each reagent, including any necessary conditions, and the type of reaction occurring. So reagent here, to get reagent A, to get from an alkene to an alcohol, you want to use acidified water. So the water will give you the OH group and the extra hydrogen to make your alcohol, and it needs to be acidified just to speed up the reaction. So reagent A is water, and a special condition would be acid. Type of reaction here, it's an addition reaction. There are 6 addition reactions in alkenes altogether. Specifically, it's a hydration, and that would be all that you have to write there. The other thing to consider, though, is that it's asymmetric addition, because water splits asymmetrically. So it splits up like that in solution, and the OH group is being added, and then the hydrogen is added to the carbon, which has the most hydrogens already, which of course is this one. So the hydrogen is added here, and then the OH group is therefore added here, and that's Markovnikov's rule. Markovnikov's rule. So they really love asking about Markovnikov and Zaitsev for asymmetric addition and elimination reaction. The second reagent, reagent B, takes us from our secondary alcohol to our secondary haloalkane. So this would be nucleophilic substitution using something like PCl3, PCl5, SOCl2, which is thionyl chloride. You could also use ZnCl2 plus concentrated hydrochloric acid, which of course is Lucas reagent. But I think that's more on the level 3 course now. And this type of reaction is nucleophilic, so just represent nucleophile like that. So a nucleophile is anything with a negative center, and it's a substitution because you're substituting the OH group for a chlorine group. So that's what you need to do for reagent B. And then reagent C, you're taking your haloalkane, your secondary haloalkane, and you're converting it back to an alkene, but this time you get but2ene. Now but2ene would be the major elimination product, because of course with elimination on a secondary haloalkane, you can have 2 possible products according to Zaitsev's rule. So the reagent, first of all, is going to be some sort of hydroxide like sodium hydroxide or potassium hydroxide. It must be dissolved in an alcoholic solvent to avoid reforming the alcohol. So you don't want to go this way, you want to go this way. And the type of reaction is an elimination reaction. A Zaitsev rule here states that the carbon with the least hydrogen is going to be the one which loses that. So you can see there it lost one of its hydrogens, and the double bond forms there. So this would be the major elimination product. So that's question 3A, part 1. And the second part here, then, they look specifically at the haloalkane and the haloalkane elimination reaction to form the alkene here, but2ene. And they're talking about reagent C. And they say circle the words below that describe the product formed. And we just said it's the major product, and it's the major product because, and this is your answer, the carbon with the least hydrogens, atoms, hydrogen atoms attached, loses another hydrogen atom, and that's Sykes-Picot's rule. Okay, so that's why you get that product, that butene as your major product there in that elimination reaction. The next part of the question, part B, it also involves schemes, and we're looking at butan-1-ol reacting with 3 different reagents here: PCl5, acidified dichromate, and concentrated sulfuric acid. And the question asks you to elaborate on the reactions of butan-1-ol with each of the 3 reagents. And for each of the reactions, you should include the type of reaction occurring and why it is classified as so, the name of the functional group formed in each product, and the structural formula of the organic product. So what I do here is I'll just draw down butan-1-ol as the central molecule of interest. So that's going to be a 4-carbon alcohol, and its primary alcohol, so the OH group is on the end. I'll just do full structural formula so we can keep track of all our hydrogens as well. So that there is butan-1-ol. And the first reaction we'll take a look at is what happens if you use acidified dichromate, CO2O72-. And of course, this is oxidation of a primary alcohol, and that will give us a carboxylic acid. So you'll have a 4-carbon chain there, and then we'll just do that properly. 4-carbon chain, 1, 2, 3. So 4-carbon chain, and then you have your carboxylic acid group on the end, and this is going to be butanoic acid. And it's an oxidation reaction because you're adding oxygen, so it's an oxidation reaction. So that's the first one. So we've stated the type of reaction, we've given the reason why it's classified as an oxidation reaction, we've named the functional group, whether it's a carboxylic acid, and the structural formula of the organic product. If you want to give more detail, you better just draw that a bit more detail. So the full structural formula is that right there. Okay. The next one we want to take a look at is what happens when you react it with PCl5. Well, we've just been talking about nucleophilic substitution in the first part of the question. So this is another nucleophilic substitution reaction. In this case, substitution. In this case, you're substituting, well, again, it's the OH group is being substituted for a chlorine. The product is going to be as follows. So it's a 4-carbon haloalkane, and the chlorine group is now being substituted for the hydroxy group. And just draw out the full structural formula here, keep track of things. But you'll also get 2 byproducts here. You get POCl3, and you'll also get HCl. You always get HCl when you're using, if you're having chlorinating agents. So there you can keep track of your 5 chlorines there, 1 and 3, 4, and there's the 5th one right there. The last type of reaction we want to take a look at is what happens if you take butan-1-ol and treat it with concentrated sulfuric acid. Well, this here is an elimination reaction. So you're removing, it's called an elimination reaction because you're removing, let's write that properly, removing water in this case. And if you remove water, if you remove OH group from here, and then you have to take a hydrogen from the next carbon, the product is going to be a 4-carbon alkene, which looks like that. And that 4-carbon alkene is back to your but-1-ene, which we had way back in part A. So that's how you do question 3, part B. There are many other questions based around schemes. So if you take a look at my level 2 organic overview video, that's you need to memorize all the content in that video to be able to answer any possibility. But they really like focusing on elimination addition reactions because it's the trickiest. So that's question 3 from the 2013 paper.